Okay, so this is just meant to be a introductory level talk, so please forgive me if you already know all this stuff. I do consider myself to be a functional programmer in the sense that I don't use variables, but I'm not like a functional programming expert or anything. So functional programming is a type of programming based on the notion of a mathematical function. How is this notion different from the more common notion in computer science? The answer is that here the function lives in a world that's completely outside of state. It's not affected by state, and it does not affect it. The inputs determine the outputs, and evaluating the function does nothing else. In contrast, impure functions can have both hidden variables and side effects. Sometimes people will point out that you can make a pure function that uses local variables. And sometimes people ask, is this not functional programming? The answer is that what you've made here is functional, but how you've made it is not. Now, why is functional programming so against variables, even in this case? Instead of thinking about references to variables, think about calling a parameterless function that's equivalent to referencing that variable. Okay? It's clear that these are impure functions if the variable's changing over time. That is why using variables is fundamentally outside the world of functional programming. In contrast, you can save intermediate results to values and then use them. Just about anything involving I/O is going to involve impure functions. Does that mean that functional programming would suggest you don't use I/O? Of course not. Instead, it just sort of suggests that you keep your use of I/O separate from the core computation in your program, which also just sort of happens to be a universally agreed upon principle of good design. More generally, using impure functions for the sake of using those particular impure functions is different than using impure functions to perform computation. And thinking about what functional programming is in comparison to the other three so-called major, there's plenty of seats up here and over there. There's a lot of them. And thinking about what functional programming is in comparison to like the other so-called four major programming paradigms, I think it's helpful to remember that there are in some ways these four things are not the same kind of thing in every sense. How a member function actually computes information, given the information inside of the object and parameters, is not a part of object-oriented programming. Okay? Instead, object-oriented programming, to actually do that, like member functions that actually compute information, given those two things, it's going to need either imperative or functional programming. And similarly, procedural programming always uses imperative programming. And pure object-oriented programming, by the way, just refers to everything being an object in the programming language. In contrast, functional and imperative programming by themselves are ways of actually performing computation fundamentally. And as most of you know, functional programming performs repeated calculations through recursive functions. One thing I want to point out here is just how important state is to imperative programming. And in fact, definitions of imperative programming involve, it uses state. There are other. You can say more about it than just this, but just one thing to think about is the only thing that can actually stop these loops once they've started is state changes. Okay? Otherwise, once it starts, it'll just run forever. So just how it performs repeated calculations, and it's the same is true of any imperative control structures, including Go2 ultimately. It's necessary for just for performing repeated calculations. What makes imperative function programming so different is not a recursion versus iteration. Recursion versus iteration involves the underlying difference, but what makes functional programming so incredibly different from imperative programming is the fact that in the functional world, everything you do in your program at every point in time, continuously, you are always creating new and more new information and never modifying anything. Okay? At every point in time, you're always creating new information. That's what makes functional programming like such a different way of thinking about your programs. Now, why are variables bad, according to functional programming? I think the answer is that it's very similar to the same reason everyone agrees that global variables are bad, and the same reason that member variables inside an object are is viewed as advantageous to the less encapsulated variables from procedural programming. One of the fundamental arguments for why object-oriented programming is good, if there's any truth to that at all, it's the same. It's the same reason there. The basic problem is, whenever you have two different parts of the program, whether it's two very distant parts of the program, or even just two different lines of code within the same function. Whenever you have two different parts of the program modifying and using the same variable, they can interfere with each other. Each one of these parts of the program has assumptions about how that variable's value is changing over time that need a hold for it to be able to do whatever it needs to do correctly. And how it modifies that variable, it can end up violating the assumptions of the other parts of the program that modify and use that same variable. In general, one of the basic principles of what is good design in computer science that people have come to is the idea of parts of your program have high cohesion and low coupling. And just thinking about low coupling for a second, different parts of your program are modifying and using the same variable. These parts of the program are coupled together. Okay? Now, in math, lambda calculus being Turing complete is like a proof that, in theory, this is never actually necessary. You don't actually have to use variables to do whatever it is you're trying to do. The coupling is unnecessary. Functional programming in practice is sort of like a practical existence proof that in practice you don't ever actually have to do this. Okay, so the coupling is higher. And this is, even if you don't think about this as complexity, this is complexity. Your program is more complex. So the coupling is higher in your computer program, and you can argue that it's unnecessary. You don't actually have to do this. I would never try to sell functional programming. I hope that it doesn't. Even though I like functional programming, I hope I don't in any ways try to seem like I'm trying to sell functional programming. If I were to try to sell it to somebody, what I would say is once I switched to stop using variables, the time I spent debugging went from a fair amount to not very much at all. Just don't get around it. I feel like I don't make mistakes, and thinking back on it, the errors a lot of times, had something to do with variables not being, what they were supposed to be. Another advantage of functional programming is, think about the name of a function and the types of its input and output. Think about that for pure functions and then for impure functions. For pure functions, it's very likely that this information will give you a good idea about what that function does. With impure functions, not necessarily. Impure functions they can be a function of far more than just this, and they can end up doing far more than just return this value. And you can say, well, that needs to be documented. It's true, all things being equal, more documentation is better, but all things are not equal between these two things. I mean, it seems advantageous that the interface of the function, tells you, gives you more, contains closer, something's closer to like all the information you know how to use it. It seems like a good thing. I mean, after all, you're using this to actually program with. Documentation is sort of separate from that. So up here, this is three functions being composed together. If this is some sort of traditional functional programming language, this is a chaining at the end of it. The point I wanted to make is not about how these functions are composed together. It's just as much as we have three functions that are clearly we're able to use together really easily. Okay, and I want to ask you to think about, how likely is it that a bunch of pure functions can be really easily used together as opposed to a bunch of impure functions. Even though the types and the semantics of the input and output information has to align, there is a sense in which just the inputs and outputs in general is sort of like a universal language for functions to talk to each other. With impure functions, they're referring to parts of state. Well, there's like an unbounded number of places in memory that can refer to. So it seems as though without additional extra work, if you want to easily compose a bunch of impure functions together, it seems as though for them to be able to be composed together as nicely as they are up here, it seems as though they're going to have to be referring to the exact same locations in state. It seems as though the more things this does, it's like more specific its use cases are. Whereas with pure functions, they're at least you have this one entry point, for input and output. That seems like it makes it more likely that the function, in general, the functions will be able to be easily used together. Now, one thing that I think is a little surprising, or I thought was surprising when I started doing functional programming, is that functional programmers today don't actually use explicit recursive functions as much as you might think. We don't write explicit recursive functions as much as writing loops in imperative programming. To understand why, first we just briefly fresh on parts of functional programming that are increasingly becoming a part of every programming language, and that is the idea that with higher order functions, you can have functions that accept other functions as arguments, and functions that return functions as their outputs. Okay? There's also this very nice syntax called lambda expressions, also known as anonymous functions, and that's where you, whenever you're passing one of its uses is when you're passing a function to one of these higher order functions that accepts a function itself as a parameter. You can basically define the definition of the function you send to it on the fly in a sometimes heavily reduced syntax. You don't have to define it explicitly elsewhere. You can define it in the arguments itself, and for a variety of reasons, the syntax is more concise. Just one of which is you don't have to give it a name. but there are others. Now, the reason you don't actually use recursion explicitly as much as you might think is that functional programming will come with a common set of higher order functions that you use to perform operations on their immutable data structures. And what these higher order functions will basically perform repeated calculations for you. The way they work is that each higher order function will correspond to some type of high-level computation on the immutable data structure, but without the details. Okay, and then the function you pass it fills in those details. The three ones that I use the most is map, filter, and fold. There's various types of fold. With map, you pass it a function which the input corresponds to one of the elements in your collection, and what this function does is it transforms a single element into something else. Okay, and then what map does is it creates a new collection with every element from the original collection transformed by this function. You pass it into some sort of new set of elements. Filter will take a function in which the input again corresponds to some element in the collection, and the output is a Boolean value. And what filter does is it evaluates that function on every single element in the collection, and it creates a new collection that only contains the elements in which that function evaluated to true. Fold is a little bit different. Here we're not creating a new data structure. We just want to compute a single value, but we want to compute the single value using every single element from the collection. And the way one of the versions of fold works is you'll pass it an initial value, and then you'll pass it a function that takes two parameters. One will correspond to an element from the collection, and the other will correspond to the accumulated result that you've computed so far. And what it will do is what fold will do is will first take the initial value and the first element of the collection and use this function to compute a value. That then is one of the accumulated result. Okay, so far. That gets passed to another execution of this function. Now on the second element, okay, that then is one of the arguments to a third call of this function that uses the third element, and so forth. Some examples of what you can do with fold is simply adding all the numbers together in a collection. If you have a tree and a path, and information corresponding to the path through the tree, you can use fold on the path information, pass it the root node as the initial value, and then pass the function that basically, from any given node, okay, and given some piece of information telling us at a certain point in the path which child to go to next, give me the child that we wanted to go to. Okay, and at the end, what it will do is it will return the evaluates to the node at the end of that path. Another example in a kind of a personal programming project I'm working on right now is so I have a labeled forest, and I want so I have a bunch of trees, okay, and I want to make a new labeled forest that has a bunch of paths added to it. So I'm basically adding paths to various trees inside inside of this forest, and I have a function called withPath that has some path. Of course, the root corresponds to one of the trees in the forest, and given one particular path, it will return a new object. This is object-oriented functional programming. Basically, I have an object and a member function already that that will return a new object with if you pass it a particular path that you want to add to one of these trees. So I can do that. The only thing I want to do here is, well, what if I have this as a piece of information that I want to pass through a function, a bunch of these paths. Okay, and this is just very simple. It just wants to call with path a bunch of times, but but understanding that this is a mutable object. So it's not like imperative. It's not an imperative world where we're just gonna change some variable a bunch of times, add to a variable a bunch of times. And the way it works is here the initial value is the object itself. This is a member function inside the class. The initial value is the object itself. The function I pass it takes a labeled for us object, some object of this class, and one particular path. Remember, we're passing a bunch of paths to this outer function. And it basically computes using this other member function, one new labeled for us object that now contains this one additional path. Okay, and then the end result of this is you'll have a labeled for us object, at the end of a bunch of uses of with path that will have all the paths added to it. Now, given that I said that you're always creating new information, and that goes for immutable data structures as well, I think it's reasonable to ask, now wait a second, is it copying the entire data structure? That some gigantic data structure, is it copying all that information every time you want to make the smallest change to it? That would seem incredibly inefficient. The answer is no. To start out with understanding why this is, the classic, most traditional list in functional programming languages is a singly linked list in which you're encouraged to add things onto the beginning of the list as opposed to the end. Okay, whenever you add something to the beginning of the list, references to the head of the original list, still, they're unaffected by the fact that you added this element to even before it. Okay, and it's able to use the list defined by this head uses all the previous structures. So all we did is we added up here. Now in this case, yes, if you add something later on, yes, copying is involved. But when it comes to trees, we're going to be able to do even better. The white nodes here correspond to some tree. And let's say we want to change this element right here to some new element. It's going to use the same idea as in the previous slide, but in the case of trees, the only nodes that end up having to be copied are the nodes along the path to the element that the operation corresponds to. Okay, and those are the only nodes that need to be copied out of the entire tree. So everything else can be shared. Now, if that sounds like a really cool idea, it doesn't have like that. That's it. Okay, it doesn't. It's not the case. You have some other data. You give me a random data structure. Well, how does immutable data structures do that with that? It doesn't. Okay, that's the trick. Okay, in general, all of your indexed data structures in functional programming are going to use that concept, and they're going to work with balanced trees underneath it all. Now, one nice thing, in general, most of your data structures in functional programming are going to be based on balanced trees underneath it all. Now, one nice thing about this is arguably the one straightforward general data structure that doesn't have any pathological behavior. In terms of all the operations that are traditionally either linear or constant, balanced trees is worst case logarithmic everything. Now, having said that, it's also average case logarithmic everything. In contrast, in the mutable world, you're going to have a bunch more choices, all of which are like best for some use case. And two of these are hash tables and arrays, which for a a lot of use, which have constant or amortized constant performance on a lot of operations, and there's only a few use cases where they're bad. In general, mutable data structures are going to be faster than the immutable ones. It's not like the immutable ones are slow. It's just that these are even better, and this is a disadvantage of functional programming. Although it does have one major saving grace, even in terms of performance. We perform, and of course, it's understood performance only matters when you need to push performance to the limit. But when you do, this is a disadvantage of functional programming. But so for like 10 years now, the clock speed of our processors is not increasing due to heat, power, and cost issues. And so instead, Moore's law ended up, he did pretty good. I think just now it's starting to like slightly, but Moore's law did pretty good. Instead, what we've been using all these extra transitions is more cores. Now, in the parallel world, in concurrent world, this issue becomes a lot worse in many cases. Okay? Because now you don't just have multiple parts of your program using the same modifying using the same variable. Now you have multiple parts of the program and multiple threads modifying using the same variable. Okay, and it's like one of the most difficult problems in computer science. Okay, with functional programming, you at least get a large class of straightforward strategies for parallelizing your program that are sort of trivial to implement. And for this reason, this is sort of hard to turn down. And for this reason, this is one of the reasons that functional programming all of a sudden is starting to, people are starting to actually consider it, using it in the industry. This is one of the major reasons. This slide showing the difference between concurrent parallel programming doesn't have anything to do with the talk. I just put it there because I like it. Functional programming, is good for both concurrent and parallel programming. One sort of double-edged sword, disadvantage / double-edged sword of functional programming is, it's very easy to compose things together. And you end up being able to do, you can do a lot in one line or 5 lines or all one line. It's not that it's less readable, because it's extremely easy to make it as readable as anything. Okay? You just gotta, when it gets to be too much, you just gotta break it down into values or additional functions, which the name makes it readable, extremely readable. But one sort of double-edged sword is it's very easy to write really unreadable stuff in functional programming. It's not easy to in imperative code to write super unreadable stuff, just because the nature of it. Different state changes aren't intimately connected with each other. Information isn't flowing between them, so they generally go one on each line. So it's harder to mess up in terms of readability with imperative code, whereas you can write really unreadable stuff, if you don't put forth a little bit of effort in functional programming. One disadvantage people say about functional programming is it's harder, or less natural to think about. The common retort to that is if you had been taught how to program in terms of functional programming, it would not be hard. And the first time I ever used fold, I had to strain to think through the reasoning. But after a few times, it became second nature. So I think it's probably the first time you learn it. It's probably a little bit harder to learn than imperative programming, but that's it. takes a little bit of effort, a little bit more effort to learn, but then it becomes just as easy. Now, when it comes to stuff like monads, there's there's seats. If you want, please sit down. That's not a seat. When it comes to monads, there's a saying that once you understand monads, you become incapable of explaining it. Once you understand monads, you become incapable of explaining it to anyone else. I think it's a concept in which you just have to first learn all the terminology. People will say when they try to explain it on the internet, they'll say the idea is really simple. It's just the terminology is hard. And some evidence is sort of true. Is before I knew much about what a monad is, I was using Scala's option, and I had no idea that it was a monad, or however you pronounce it. And I eventually discovered these like really, really, really cool member functions of it. That did all these like really cool stuff. And it turned out, and it's really easy. You can explain it really simple. It's not hard at all. And it turned out those were the monadic functions. So now I want to talk a little bit about object-oriented functional programming. I want you to think about a constructor as a function that returns an object, and I want you to think about think about a member function as a standalone function of both the object and its parameters, and ask you to think about what exactly makes these impure, not pure functions. And one answer is obvious. It's the member variables of the object. There's another more subtle one, and that is a constructor returns an object each time, and with respect to the object identity, even if there's a sense in which every object's return is a totally separate object, even if the parameters, the arguments to the constructor are the same. Okay, but let's say we get rid of member variables, just have member values, and let's say we discard or not use discard or not use the object identity. Okay, in that case, we're going to have essentially pure functions. So it's a mixture of object-oriented and functional programming. Java's string is an immutable object. Has all these member functions that do operations on string, and every single last one of them returns a new string. There's no way to modify the object.
That's the same thing.
Yeah. It's kind of interesting. This. I mean, now I understand why now they'd be adding it in. It's interesting. At the very beginning of Java, they made it that way. I'm sure there's some reason for it. So what you do to do immutable instead so what you'll do in immutable object-oriented programming is instead of having member variables and mutator member functions that modify those variables, we're just going to have member values, and we're going to instead have member functions that instead of mutating the now non-existent member variables, the equivalent functions over here is going to return a new object of this type whose information will correspond to the equivalent change that happened over here in the same object. And this is just sort of a small note, but one sort of clever way that some people came up with in functional programming to make this type of transformation very easily. And you could have this as a member function of the object, or you could just use it internally. But if your language has both default values for parameters, where if you don't pass it an argument matching that type, you'll be assigned to a default value that was made by the person who made this function. If it has default values and named arguments, where you can now all of a sudden change. You now change the order of the order in which you pass arguments to a function. You understand you have to actually explicitly name what you're sending it because it's now no longer in the order. If you have both those things, what you can do is you can make a copy member function in which the parameters all correspond to the member values of the object, and they're all assigned equal to the current objects. The default values of these parameters are all assigned equal to the member values of this current object. And so if you call copy without passing any arguments, it will just return a new object that has identical information. But you can also make changes really easy by just specifying the member values you want to change and saying equal. I want this parameter corresponding to that member value to be equal to this value instead. It makes it very easy to create new objects with certain changes. Now, people will say that the difference between object-oriented programming and functional programming is that the data and functions are tied together, whereas in functional programming you keep it separate. This is true, but I think it's a little vague. And the reason I think it's vague is think again about a member function, okay, versus a standalone function has the exact same behavior, okay, but it's a standalone function of both the object and its parameters. Okay, as tempting as it is to say this captures the difference between object-oriented and functional programming, doesn't matter how much it looks like it does, these two things are almost the same thing. And this just simply does not capture the difference between object-oriented and functional programming. To understand what does, I think you first have to remember that you can do a rudimentary form of object-oriented programming purely with standalone functions and conjunctive data types. Okay, so you can do a rudimentary form of essentially object-oriented programming, even like languages like C, with their structs. And now thinking about it in that sense, thinking about we can do object-oriented programming with stuff like this. I think it allows you to understand what the real difference here is that in object-oriented programming we are, and specifically I'm talking about immutable with respect to immutable objects over here. We're really going after these conjunctive data types, and we're making creating them, and we're making functions in terms of them. Okay, even when the actual behavior of what that member function does only corresponds to some information inside of this conjunctive data type, we're nevertheless making the function in terms of in terms of this object. It's a member function of this object, and it returns an object of this type, even if just one piece of information changes within it. Or if you want to think about in terms of the mutable world, it's changing an entire object as opposed to just producing a small piece of information. So it has something to do with the essence of object-oriented programming. In functional programming, you still have conjunctive data types and you still use them, but there's a tendency, if you view a spectrum here, there's a tendency to do more of this, where you make functions in which the input-output types correspond more closely to just the information that actually corresponds to what this function is actually doing. So over here, in this function, X changed, but Y didn't. Over here, we have a standalone function that doesn't involve Y at all. And I think that functional programming is going to, traditional functional programming is going to tend more towards that, whereas at this extreme, it's just object-oriented programming. Now, what's the utility of these different approaches? The utility of the traditional functional approach is pretty clear. This is more composable. Okay, if this behavior is useful to some other part of your program or some different part of your program altogether, the only requirements, this function is easy to use because the only types it involves is it's like the minimal piece of information. if the behavior is useful, the behavior involves those types of information, and that's all you need. That's all the function involves. And that's all you need to know, that's all you need to use to be able to use the function. With object-oriented function, the same function over here, the member function, to use the behavior, you're going to have to use that object type and everything that comes along with it, which may be a lot of things. Not only is you have to construct an object with a bunch of other pieces of information, it may require even more than that. It may require using several other member functions first. So this is more composable, but many people, including myself, still feel there's something good about object-oriented programming. There's something appealing about thinking about your program to a lot of people in terms of objects. If I had to guess, two guesses to what psychologically it might involve, even though you're still using conjunctive data types over there, here you're using a lot. This is at a higher level of abstraction, this higher level data type, like bank account as opposed to customer ID. This is a higher level of abstraction, and you're not just making these. You're also using them more because you're making your functions out of this higher level data type. So you're more working with a higher level of abstraction over here. The higher level of abstraction may be more appealing. Another thing that's going on is a lot of these member functions in the object-oriented world it's in sort of correspond to an algebra. You have this object type you've created, and now you have transformations between different values of this object type. Whereas over here, it's oftentimes functions from some piece of information to some other type of information. Here it's more like an algebra. That may have something to do with what's more appealing about it. And I think it'd be better to stop here. Just a few things to know. Let's just stop here.
You sure you want to stop here? Sure. We can go like 5 more minutes unless we get a lot of questions.
Okay. What was I going to say? So I'll just say two things. This kind of personal programming project I am making a labeled forest. So I'm making a forest, but I'm going to embed these in I have a bunch of forests in a larger, interconnected in a larger graph. So altogether, it's not going to end up being a forest, a bunch of trees. It's going to be a general graph. Some people have said that it's kind of weird to it's kind of graph algorithms and functional programming are kind of weird, and maybe super optimized versions are. I don't know, but I eventually found a pretty nice way of doing it. Instead of dealing with links between nodes, because you can't mutate them. Even if you change, like if you imagine a node object that's pointing to another node object, even if you take that out and put another node in, it's also pointing to that same object or some other object. You now have a problem. Every other node that was pointing to the node you removed, now you have to update all of that. You have to change all of those to this. And the problem is that you then create the same problem over here. You end up having to change everything. This has nothing to do with graphs. This has to do with how do you implement a doubly linked list in purely immutably. I mean, you have to do something special like what we went over on with earlier. The solution doesn't exist for general graphs. You can do that on trees, but you can't do that on everything. In the mutable world, it's easy. You just change you don't even have to change like the node object. You just change the reference. Okay, it's a variable. But there's something that's just as easy. You just have to understand you don't use the references. And it's kind of ironic. It ends up being more about information as opposed to specific objects. What you do is or what I did anyway, you give each node some sort of identifying symbol. I used a long. Okay, that's its that's like sort of the ID of the node. And then you represent the structure using this identifying information. For instance, each node has the connectivity is represented by a collection. A node will have like a collection associated with it that's that contains what are the IDs of the other nodes that's adjacent, and then to efficiently be able to access these nodes and jump around, you just have a map from the long identification number of the nodes to objects that store the information about the nodes, and that you can do immutable transformations on this map. Changing certain nodes, changing out the information associated with each node, really easily. That was one thing. So the point I was trying to get at is that even though in some ways you're limited in terms of the data structures you can use in functional programming. In some ways, okay, if you ever want to create a new data structure, once you have lists, indexed lists, sets and maps, these are very powerful. You can make other data structures using them. Math corresponds to functions in mathematics, and mathematicians do all kinds of things with functions. Similarly, the math ends up being very useful. So once you can make other data structures out of these very powerful primitive ones. And then the other thing I want to point out is this is actually a private constructor. So in Scala you have a primary constructor, and you can actually in Scala you can make it private. And what I'm doing is the member values, I made them private as well. And so I just like you can have an internal representation in with traditional objects, you can do that with immutable objects as well. And then I have an auxiliary constructor that's actually public. And so they don't no one else knows what this information is, and they don't manipulate the object, by having this information and passing it to it. So just like you can control, maintain consistency properties by defining this is the only way the object, with traditional objects, this is the only way that the member variables can change. So with these member functions, and you can enforce certain properties will hold. You can do that with immutable objects as well, because the only way is to change. It's not like they have this information, the internal representation, and they can change it however they want and then pass it to the object, and me have to check possibly to make sure that this certain properties I want to hold actually hold. You can still make this information private, and that was just another comment.
Questions?
What drove you to move to functional programming?
That's a very good question. All right. I think the answer to it is interesting. So I used Scala. I wanted to use Scala because I wanted to use. I didn't like the verboseness of Java. Scala is a really nice syntax, and then I think this is the reason why Scala became. Martin Odersky wanted Scala to be a functional programming language. He wanted to combine object-oriented and functional programming. Think about how did he actually get it? It's a very multi-paradigm language. It's not like the other functional programming languages. How did he actually get the community to be functional? Is it he just said, "Hey, use this functionally"? I don't think that would work. I think that the reason I got the answer to your question is that it's also I think the reason why he was able to achieve this. And I guess it wasn't a lucky guess. I think he's a very smart guy who came up with this idea. So the immutable data structures in Scala both have the same names, the ones from the Scala API. And the immutable ones are imported by default. So if you don't want to learn about functional programming, you have to add import statements. And very quickly, I didn't want to do that. And I just started looking at the immutable, those map, fold, and try to learn how to use these immutable data structures. And I learned, hey, I like this better. And then that's how I got introduced to. I studied functional programming very briefly in college, but then that's how I started using it, and I just liked it better.
Do you think it's more efficient? I know you said that the debugging's less for obvious reasons. If you were writing the same thing in Java, given over a period of time, if you were, expert programmer in Scala versus Java, is one overly more efficient than the others from a programming perspective and over time?
In terms of productivity?
Yep.
Initially, when you're learning functional programming, you're going to be less productive. But the more you learn it, you definitely become as productive. I'm hesitant to say, it's a very deep question. I'm hesitant to say which one ultimately is more productive in when you have two experts.
Sure.
I don't know the answer. But initially, it's going to take time to to learn and become better at it. But you do not too long become you become just as productive, if not more productive. I don't know which one's better in that sense.
Do you have a trade-off in performance by using functional programs? Since basically you have to create everything new if any information changes. So I was thinking like in C#, string versus string builder. Normally, the string builder is used for areas where there's a lot of string manipulation, and you want that to perform and not crash because you're running out of memory or something like that. So, but I can imagine that performance for something like this on like parallel processing, there's maybe some advantages there. So just want to know your thoughts on that on the performance side of things.
So you have that immutable structure difference, but I think you're asking not about data structures, but more generally, and it's a very good question because unlike the data structures that we talked about, where it doesn't have to copy everything. When you're using immutable objects, it's not that you are actually every single time you do the equivalent of a mutator method, you are copying all of the information. Additionally, so you are copying all the information every single time you do that. That is more efficient. You also you have a lot more function calls, and when the recursion doesn't end up being tail optimized, you have a lot more function calls. So you have a lot more a very much larger amount of constant overhead. Now, on the other hand, functional programming is like an algebra. Everything's like an algebra that can be. It's literally an algebra. It's kind of like with database queries, SQL queries. It's an algebra that can be heavily optimized. The most powerful optimization technique is laziness. So functional programming has this. This is just the nice name. Functional programming has ways in which it tries to make up for that. In practice, it's ultimately slower in general. Single-threaded performance in general, these optimization techniques tend to not make up this huge overhead that exists, and functional programming tends to be slower in general. Its big saving grace is that the problems with dealing with variables reach a critical mass where people stop caring about trying to optimize imperative code in many multi-core settings, and they don't care that you can be faster with imperative code, and they want to use the functional programming in multi-core situations where performance, ironically, does matter a lot. But it's a disadvantage. I mean, just to give you one example, people don't make people don't make computer games using functional programming.
I think you can save a lot of time just with one line of code because you're getting rid of the too much ceremony in order to use a function. That's pretty. I mean, in my opinion, it's one of the things that I really like. The other thing I see is it's at least I haven't seen a technique to have really complex tasks within functional programming.
Yeah, it does. You said listen as a disadvantage.
Yeah, like if you want to have a complex task within a function, I mean using functional programming is not really easy to perform that.
Yeah, I mean, you're absolutely right. There are difficulties that he is right about that I didn't really cover. Like there are parts of functional programming that are hard, now giant programs still are very complex in any sense, but yeah, it's what he's saying is also a disadvantage of functional programming.
All right, last call for questions. If you did not sign in, I'm going to put this laptop by the feedback jar. Please give us your feedback. Green is good, red is not good, yellow is in the middle. And don't forget to sign in. Thank you again to Noah. Round of applause.